So share screen here.
I'm Miguel. We're about ready to get started.
All right. Okay.
I'm Miguel. We're about ready to get started.
So it looks like, well, according to my time, I've got about 30 seconds. Okay. So
I'm Miguel. We're about ready to get started.
So it looks like, well, according to my time, I've got about 30 seconds whenever you're ready as well. So
yeah, I'm Miguel. We're about ready to get started. We are actually starting exactly on time.
Well, according to my time,
and I'll do a little quick intro for you.
Ready as well. So
yeah, I'm Miguel. We're about ready to get started. We are actually starting exactly on time.
Well, according to my time,
and I'll do a little quick intro for you.
So
yeah, I'm Miguel. We're about ready to get started. We are actually starting exactly on time.
Well, according to my time,
and I'll do a little quick intro for you.
So
yeah, I'm Miguel. We're about to get started. We are actually starting exactly on time.
Well, according to my time,
and I'll do a little quick intro for you.
So
yeah, I'm Miguel. We're about to get started. We are actually starting exactly on time.
Well, according to my time,
and I'll do a little quick intro for you.
So
yeah, I'm Miguel. We're about to get started. We are actually starting exactly on time.
Well, according to my time,
well, if you're just joining us, welcome to Astronomy. Yeah, I'm Miguel. We're about to get started. We are actually starting exactly on time.
according to my time,
well, if you're just joining us, welcome to Astronomy. I'm Miguel. We're about to get started. We are actually starting exactly on time.
according to my time,
well, if you're just joining us, welcome to Astronomy. I'm Miguel. We're about to get started. We are actually starting exactly on time.
according to my time,
well, if you're just joining us, welcome to get started. We are actually starting exactly on time. well, if you're just joining us, hundreds of years, astronomers have been looking at the universe with light. Bridging fundamental aspects of gravity with astrophysical interactions in related environments. Hundreds of years, astronomers have been his tenure here looking at the universe very, very productive, and we're sad, but at the same time excited to see him go on to new things, and excited to see what his fundamental aspects of gravity. We like to also throw in one fun fact about related environments. Looking at the universe for very, very productive, and we're sad, but at the same time excited to see him go on to, and I'll switch to Miguel's slides, new things, and excited to see what his fundamental aspects of gravity. We like to also throw in one fun fact about related environments. Looking at the universe
very much thank Alvin for
sad,
organizing
excited to see him go on to, and I'll switch
this
to
Astronomy on Tap,
new things, and excited to see what his
inviting me
fundamental
to
aspects of
give this
gravity.
talk.
Also throw in
So
one fun fact about
today I'll be talking about which is a little bit on like as a graduate student. Very much thank Alvin for also being nice and continuing to work with this Astronomy on Tap stuff. And for inviting me to our episode. So today I'll be talking which is a little bit on first being as a graduate student, gravity space out curvature, or also being nice and continuing to gravitational waves to work with this Astronomy on Tap stuff. For inviting me to our episode. So today I'll be talking which is a little bit on first being as a graduate student, gravity space out curvature, or also being nice and continuing to gravitational waves to work with this Astronomy on Tap stuff. For inviting me to our episode. So today
Try that again, Miguel. I suspect that what was happening was that I had my own YouTube window with you talking open, so it was picking up the audio from Zoom, but also the YouTube stream and trying to broadcast both, hence the looping. Sorry about this, folks. We're absolutely working to get this right the first time and process by trial and error.
Yeah, I've also been looking at some messages I've been receiving regarding audio looping. So hopefully we'll get some feedback from the audience if the audio's all right now.
You should go ahead, Miguel.
All right. Okay. All right. So, right, again, I'll thank Gautam for organizing this online live stream and inviting me to give a talk. So this is a talk on ripples in space-time towards the detection of nanohertz gravitational waves, and it'll touch on some work that I did as a graduate student and work that I'll be continuing to do as a postdoc. Okay, so starting from the basics, starting from some major takeaways for this talk. Gravity is a space-time curvature, and with this space-time curvature, waves can be produced on these spacetimes, and these are known as gravitational waves, and they provide us a new window into the universe. And so This is a new messenger with which we can probe the universe, whereas, as Kathleen mentioned, electromagnetic waves have been one of the main messengers that have been used in the past century for probing the universe. And the next 2 points, gravitational waves span a range of frequencies, so there can be low frequency gravitational waves and higher frequency gravitational waves, and I'll describe later in the talk how these different frequencies correspond to different masses for the binary sources that produce these gravitational waves. And then the last point, which this talk will mostly focus on towards the end, which is on nanohertz gravitational wave astronomy and how that is on the horizon in the near future, so within the next few to several years. Okay. So starting from the very basics, so Newtonian gravity. So Isaac Newton's perspective on gravity is that it is a force between massive objects. So if I have two bodies with finite masses, they exert a mutual gravitational force on each other. And this force is proportional to the distance r between these two massive bodies. So the gravitational force between these two bodies gets weaker at larger separations. And that's been mostly been the view of gravity up until Einstein in the early 1900s. So Einstein's view of gravity is that gravity is space-time curvature. And whenever some body has some finite mass or mass energy, that mass energy deforms the space-time. And what that does is that space-time will tell matter how to move, but conversely, matter tells space-time how to curve. So the reason the Earth orbits around the sun is because the Earth is within the sun's potential well, and also we are within the Earth's potential well, so we are bound to the Earth gravitationally. And so the strength of gravity depends on how much mass there is, and also how tiny that mass is packed into a given amount of space. So for example, the sun deforms space-time with its mass energy, but if that amount of mass is packed into a smaller space, say into the size of a neutron star, which is something like 10 kilometers in size, so comparable to, say, the size of Chicago, then the gravity there is much stronger due to that higher compactness. And if that mass is packed even more compactly into an even tinier space, such that the mass of the gravity becomes so strong that the body then collapses due to that gravitational attraction, then what's formed would be a black hole where the escape speed at, say, at some distance, well, of course, the characteristic distance being the Schwarzschild radius, at that distance, light, not even the escape speed would have to be something like the speed of light in order for to escape such an object. And also quite recently, we've now been able to image supermassive black holes. So the Event Horizon Telescope is a collaboration of an international collaboration of radio telescopes and people as well, working on the theory, data analysis sides, and the data acquisition sides to image on the right here this radio image of M87, which is a supermassive black hole sitting within a large galaxy. So what's shown here is the radio image, and you see this dim region towards the center. So that region is the supermassive black hole, and surrounding it is the disk of gas that this supermassive black hole is accreting from. So there's this brighter region of the radio that might correspond to the gas that's moving towards our line of sight. So it's getting Doppler beamed and brightened. And so supermassive black holes are thought to reside in the centers of galaxy, and of course M87 is certainly one of them. On the left-hand plot is M87 at different length scales. So you see the EHT image of the central supermassive black hole in the corner on the left there. And that's corresponding length scale there shown in below the image is about something like 0.003 light years. If one were to zoom out, you would be able to see the jet morphology. So as the M87 black hole is accreting, it's also spewing out high velocity gas, and that's also emitting in the radio and emitting these luminous jets that we're able to see with HT. And zooming out even further still, we're able to see the jet morphology influencing its surroundings on larger and larger length scales. So you see to the right is the fully or more zoomed out image, which is 100,000 light years in length scale about. And you compare that length scale to the length scale, so the Schwarzschild radius of the M87 black hole. If you recall, that's 0.03 light years. So there's about 8 to 9 orders of magnitude here in length scale. So this very massive supermassive black hole, it's very small in size, but it's also influencing quite a large influence on its surroundings by creating gas and spewing out these large-scale outflows. And on the right is the corresponding image, but also it's overlaid several wavelengths here. So red is radio, purplish is X-ray, and then optical is the yellowish-green colors. So notice the reddish morphology on the right seems to have has some similarities to the image shown on the left as well. So that reddish morphology is the radio emission, corresponding to what we think are electrons accelerating in the magnetic field geometry of this black hole and its surroundings. So what if there were 2 supermassive black holes in orbit? So that's certainly possible, given what we know so far about cosmology and galaxy evolution. And how do we know that? So we've observed galaxies that can merge over cosmic time. On the left is some observed images of galaxy mergers that are interacting. So I have 2 panels here, top and bottom. So these are galaxy at the top panel is 2 galaxies at close separation, and on the bottom is, see, there are 2 galaxies merging. So we definitely have circumstantial evidence that galaxies do merge over cosmic time. And on the right is a schematic of how we think that galaxies evolve, and we think they evolve by merging with other galaxies over cosmic time. So as structures form in the universe, gravity causes gas to collapse and form galaxies, and then gravity causes galaxies to merge with each other, and these galaxies merge over cosmic time and get larger and larger in mass. So a main question is, since we know that supermassive black holes mostly reside at the centers of galaxies, do the central supermassive black holes also merge? And when we have massive bodies in orbit, those produce gravitational waves, which are the ripples in space-time that are produced from the motions of these massive objects. So on the left is an animation showing how the orbital motion produces gravitational waves. So as the body orbits, waves are produced in the surrounding spacetimes, and these waves propagate away at the speed of light in general relativity. So that's what it looks like on a imposed on a 2-day representation of the wave propagation. On the right is what the waves would do, or a representation of what the waves would do in a 3D space-time. So this is a series of rings, and as a gravitational wave passes by these series of rings, it causes these rings to stretch and squeeze. And that stretching and squeezing comes from the gravitational waves that are produced from sources like those in the left. And black holes can span a wide range of masses. So I talked about the supermassive black hole binaries. So those are of order 10 to the 9, so billions upon billions of solar masses. And towards the left of this diagram here So 10 of order 10 to hundreds of solar masses, those are stellar mass black hole binaries. And those are currently being detected by the LIGO-Virgo collaboration using a technique called laser interferometry, which I'll be describing later in the talk. So on the right, in order to detect supermassive black hole binaries, the current detection methods that are being used for these gravitational wave sources are pulsar timing arrays. And I'll go into more detail later in the talk as well. So in the middle, bridging these two mass ranges, so stellar mass to supermassive, it's thought that there might be intermediate mass black holes. So black holes ranging from 10 to the 3, so maybe around 10 to the 3 to 10 to the 5 in solar masses. But there is some indirect evidence that these might exist, but we don't have yet a direct detection of intermediate mass black holes. And that certainly is something that opening up the full gravitational wave spectrum hopes to reveal in the coming years as well. And given that black holes span a wide range of masses, that corresponds to a spectrum of frequencies. So from going from left to right is going from low frequency to high frequency. And the high frequency end is where LIGO-Virgo is currently operating and detecting the mergers of stellar mass black holes, neutron star mergers, as well as possibly even neutron star black hole mergers. So those frequencies are order 10 to thousands of hertz. And for the supermassive black hole binary part of the spectrum, there the wave periods are of order years, and that corresponds to about 10 to the minus 9 in hertz, so nanohertz frequencies. So in order to detect supermassive black hole binaries in that part of the frequency spectrum, that requires the precision timing of millisecond pulsars. And to delineate or differentiate between those two methods, so laser interferometry for the the high frequency part of the spectrum, how that works is that this is a laser interferometer schematic shown here. A laser is shot and then split into two with these mirrors. The mirror bounces off of one end and off the other end. And if a gravitational wave happens to pass by, that would cause the arms of this interferometer to squeeze and stretch differently. And that squeezing and stretching differently causes an interference in the detector. And that is how gravitational waves are detected with this laser interferometry method. On the pulsar timing array end, here, instead of lasers, you're using pulsars, which are rapidly rotating neutron stars. And we see these very regular pulses coming from these pulsars in our galaxy. So you can think of each pulsar as being almost like a laser arm, where if the gravitational wave passes through this system, then the timing of the pulses changes. The timing of the pulses changes due to the gravitational wave stretching and squeezing of space-time. So it's analogous, almost analogous to a laser interferometer, though there are very deep, subtle differences between these two detection methods. And going a little bit more into the pulsars, they're rapidly rotating magnetized neutron stars. If you recall, neutron stars are of order 10 kilometers in size, so something like Chicago. And given that pulsars are magnetized, they thought to have these radio beams that when the pulsar rotates, the beams pass along our line of sight, and we see that radio pulse coming from the rotation of this pulsar. And these spin periods can be something like of order seconds to milliseconds. So really fast spinning neutron stars that we see these very regular pulses from. So these pulsars were first detected in the late 1960s by Jocelyn Bell Burnell. She was a graduate student back then who very much led the building and building of the radio array and interpreting of the data. And more recently in 2017, so this was a picture I had taken back when I was doing a study abroad at the UK, but this was an IOP gathering of the Women in Physics, so Institute of Physics. And this is where I was attending a talk where she was being awarded the IOP President's Medal, being recognized for her work on to detect pulsars. So there's one in the North America, that's the nanograph collaboration. And then there's the European one, the European PTA, and one in Australia, the Parkes Pulsar Timing Array. And there's also pulsar timing arrays being established and progressing as well in South Africa, India, and China. So this is an international collaboration that's pulling together resources and methods to detect nanohertz gravitational waves from supermassive black hole binaries. And so this is just a schematic show or an artistic impression of how the pulsar timing arrays work again. So gravitational waves are produced from the orbital motions of massive objects, in this case, supermassive black hole binaries. Those waves propagate away from that gravitational wave source, and as they pass through a pulsar timing array system and the Earth, causes the timing of the pulses to vary due to that stretching and squeezing of space-time. And so pulsar timing arrays hope to see that correlated stretching and squeezing eventually in the coming years. Have we detected anything yet? No, but hopefully soon. So the sensitivity of the pulsar timing array depends on how many pulsars are in the array and how long you observe them for. So definitely adding more pulsars to the array, as well as observing longer, will improve the detector sensitivity and hopefully to the point where the gravitational wave detection is made at the nanohertz frequency end of the gravitational wave spectrum. And even though pulsar timing arrays have not detected nanohertz gravitational waves, the upper limits that are set are still astrophysically constraining and useful. So this here is a telescope observation of a quasar. And a quasar is a really bright active galactic nucleus, which is basically a bright object that's thought to come from a supermassive black hole, like something like M87 that's accreting and spewing out jets and this very bright emission. So what's plotted here is the brightness as a function of time, and the blue and black data points there are the measured data for this quasar. And then there's two models here, one that is red and transparent. So that is a model corresponding to brightness variations from the accreting, from a single accreting black hole, while the opaque solid red line is the brightness variation predicted from binary motion. So if there was a binary, perhaps the brightness variations that the data or possibly the variations the data show might be corresponding to binary motion. But as you can see here, the transparent red line or red curve and the opaque red curve are pretty much can't be distinguished just from this data set here. It almost looks like both of them can represent the data quite well. So this data is not conclusive enough to say that this is indeed a supermassive black hole binary. And there's been a number of surveys that have been building up a catalog of these kinds of quasars with periodic variability. So what fraction of these could be real binaries? And pulsar timing arrays have provided upper limits on what the gravitational wave background can be. So what you can do is take all the candidates that these periodic quasar candidates and see what the gravitational wave signature might be from an ensemble of these. And these produce, the exercises, these produce a gravitational wave background that is larger than what the PTA upper limits are, then definitely some fraction of these candidates can't be real binaries. So that's one way in which pulsar timing array upper limits, i.e. a non-detection, has been used in astrophysical research currently. But what will we learn from an eventual detection? So as I mentioned earlier before, gravity gets weaker at larger separations. So from that point of logic, it certainly isn't easy for supermassive black hole binaries at wider separations to get to the close enough separations where gravity is strong enough such that gravitational waves can then bring the close binary to merge. So the schematic here is that you see this galaxy image here with two bright points. That corresponds to two active galactic nuclei, so two brightly emitting supermassive black hole binaries that are accreting. They're at these wide separations, but in order to get to the close separations where gravitational waves start to dominate the in-spiral, there's a number of environmental effects and astrophysical interactions that might be needed in order to get from the left to the right on this in the schematic. Another thing we might learn is how supermassive black holes might co-evolve with their host galaxies. So there's one popular point of research in the galaxy evolution community, and that is that black hole masses appear to be correlated with the mass of the central bulge. So this is a galaxy property. So the more massive the central bulge of the galaxy is, i.e. the stellar mass of the bulge, the more massive the black hole is. So this correlation hints that perhaps there's this interplay between the supermassive black hole that lives in the galaxy and then the galaxy as a whole. If you recall from the previous M87 image, we saw this large separation of length scales where the M87 black hole was spewing gas out to these very large distances and influencing over a large characteristic length scale. So that's also a hint of this interplay between the very small supermassive black hole at the center of the galaxy and the very large galaxy length scales. And the future shows promise for gravitational wave astronomy at multiple frequencies. LIGO Virgo and Pulsar time arrays are currently in operation. And on the right here is the gravitational wave spectrum, but also on the y-axis being the gravitational wave strain. So change in length over length. So for example, 10 to the minus 15 is something like, if you had a change of 10 to the minus 15 in 1 meter, that corresponds to changes in length less than almost well of order the size of an atom. Or sorry, the size of the atomic nucleus. So almost femtometer type changes on meter length scales. And so you recall the gravitational wave frequency spans from low frequencies to high frequencies, with LIGO being on the very high frequency end, and Pulsar time array sitting at the nanohertz frequency part of the spectrum. Pulsar time arrays hope to detect gravitational waves in the next few to several years by adding more pulsars to the array, as well as observing longer. The LISA space mission is planned for the 2030s, and that'll open up the millihertz part of the gravitational wave spectrum, and that will reveal to us the mergers of these supermassive black holes, as well as stellar mass compact binaries at wider separations. And there's also the next generation ground-based detectors planned for the 2030s. So improvements to LIGO that will help probe deeper or farther out in cosmic distance and corresponding to farther back into the past of the universe. And so as a summary, going over the main points of the talk. So the main points being that gravity is space-time curvature, and waves of gravity can propagate on the space-time curvature, and these gravitational waves provide a new window into the universe. Given that black holes span a wide range of masses, that corresponds to gravitational waves spanning a wide range of frequencies. So from the high frequency end of LIGO to the very low frequency end to nanohertz, like pulsar time arrays that are currently operating as well. And then nanohertz gravitational wave astronomy is on the horizon, with a detection hoped for in the next few to several years. So definitely keep your fingers crossed and your eyes peeled for any new developments from pulsar time arrays. And so with that, I'll end there. And happen to take any questions from Gautam or the chat. And thank you for your time.
Thanks so much, Miguel. Since the intro got cut off right at the beginning with our audio issues, I do want to sort of like reintroduce Miguel right at the end of his talk. So Miguel is one of the very few astronomers in the world who is now using gravitational wave astronomy. For hundreds of years, astronomers have used visible light and electromagnetic radiation across non-visible parts of the spectrum to study our universe. But it's only very, very recently, in the last few years, that gravitational wave astronomy has really taken off with the detection of binary black hole systems through LIGO. And Miguel's really part of this revolution. We're incredibly proud of him here at the University of Illinois. He is our latest PhD graduate. And we're sad to see him go, but we are excited to see all of the great things he goes off and does. And his first stop is Carnegie Mellon University. So if you're in chat, please do give Miguel a virtual thumbs up for all of his hard work here. And we look forward to seeing what he does in the future.
Great. Thank you, Gautam.
And if you have questions for Miguel, we'll take them for a little bit on the YouTube channel. This is much more informal. So if you also want to use Slack or something like that to send me a question for Miguel, that's totally fine. So one thing you mentioned, Miguel, was about pulsar timing arrays versus interferometers as entirely different sort of systems. What are the fundamental technological differences between them? You have this concept of interferometry, which I think people who've taken physics are familiar with, but what's happening with pulsar timing arrays? And after that, I have a question for you from Michael Smith on YouTube.
So right, the pulsar timing arrays, that involves observing the arrival of pulses from pulsars using these radio telescopes. So if you recall,